Hi, welcome back. This is our session 2, where we're going to talk about sequent peak analysis in R. The code that I'm going to be developing here today is probably not the most elegant R code at all, but it works, and it will basically show you how to do some for loops, if statements, and basic engineering calculations that you would have in a spreadsheet that you can easily convert to R. And I think that that's one of the best ways to get started using a particular programming language is you're already used to doing something in a spreadsheet. So can you move it over to a programming language effectively? This assumes that you have some basic understanding of the sequent peak method, but I'll explain enough of it as you go along that you can follow along pretty easily. I have the code linked in the description and on my website, but we'll just be developing our own version of the code here together in the video. Today, what I'm going to do, instead of running all the commands in the console like we did last time, was that I'm going to go and actually create a new file. And this allows us to write the code in the upper portion here, and then we can run it. And we can also try out different things in the console as we're going along if we want to test things out. This is based on an example that's in the Laux and Van Beek textbook, and I'll also put a link to that in the description. And it basically says that there is a sequence of inflows into a particular reservoir, a reservoir that doesn't exist yet. We're trying to figure out how big we want to make the reservoir. Given that you have a certain sequence of flows on a river, how can we store water? How much do we need to store to be able to release the water at a constant rate and not, have everything go dry? So the reservoir is going to supplement the storage as it goes along. I'm going to create a vector that has the information in it, and we'll say that it just essentially is concatenating a series of numbers together. There's nothing special about these numbers, but I'm just following the Laux and Van Beek example. Now, you'll notice, so essentially just in generic units, 1, 3, 3, 5, 8, 6, 7, 2, 1. Now, eventually we will want there to be 3.5 units released from this reservoir. So that means that in the first time step, the second time step, the third time step, there aren't going to be enough, and there you would be releasing from storage, and then you get some ability to refill in the next couple of time steps, and then it starts to go down again. It is interesting, and probably the people that created this example did it this way for a reason, is because you'll notice that the lowest parts are at the beginning of the vector and at the end of the vector. If this is a particular sequence that repeats over and over again in an annual cycle, the real pain points are going to be at the beginning of the sequence and the end of the sequence when those low flows are all combined together. Therefore, in the sequent peak method, we want to double the time series. And doubling the time series allows us to create a sequence that ends up being more severe than just looking at the sequence by itself. I will call the full length of the time series, I'll use the term full. Remember, there's nothing special about these variable names. It's just nice to be able to have a descriptive variable name so you don't get confused later. You'll also notice that I'm using an equal sign instead of the arrow operator. Well, it turns out, and I have a link in the actual code, that for basic stuff like this, it's fine to just use an equals. There's a historical reason why we had the arrow operator, but I always forget to use it, and so we'll just use the equals from here on out. And this C operator can be used again. So the C operator says to concatenate these lists together, and I can just say that I want 2 copies. So I can say run selected lines. I had to look for a second at where it was. So if I run selected lines, what it does is essentially copies and pastes what I have in the script and runs them in the console. And then you can see that my original sequence was 9 members long, and then now I have a sequence that is 18 members long, and it just repeats. And so those low flows are bumping up against one another here. I want to be able to write this script so that if I end up changing what's over here in line 1, that I want the rest of it to really work. So I don't want to hard code the number of sequence steps that I have, because I want this to be working even if I had a series of 28 numbers or something like that. If I play my cards carefully, I'm not going to need to change any of the code. And that's why line 3 is going to work no matter how big Q sub t actually is. I'm going to save myself some work by actually creating a variable called the number of steps, num underscore steps. And I'm going to say that that is the length of Q sub t sub full. And then if I were to run this, it would evaluate to the number 18. That way, there's going to be calculations I'm going to need to do that are going to be 18 steps long, and I can just say that they are num steps long. The rest of the information in this calculation, we've got Q sub t, which is the inflows, and then we've got the releases. And I'm already violating one of my rules, which is that I should comment my code. So I'm going to put in a comment that says that this is inflows, a doubled sequence of inflows up here, the number of steps in the doubled sequence. So now that we've doubled this sequence, everything else that we're going to do is also going to be doubled, and everything will, have 18 steps in it. So the number of steps is stored there. And so now we input the rest of the information, which is the desired releases. Okay. And so the desired release, actually, I should say, is 3.5 units per time step. We are making this reservoir because we want there to be 3.5 units of water in every time, but we can see that there are not that many units of water. The release is going to be R, just following the book. And I'm going to use the same word full here just so that I can keep track of, the fact that it's the same length as the doubled sequence. The command rep allows us to repeat a number and create a list that has the same number over and over again. So I'm just going to go ahead and say that I would like to repeat 3.5. And how many times do I want to do it? Now, I could say length of QT full. I could type in the number 18, and both of those would work, but I want to try to be consistent, so I'm going to use this variable that I've created, num steps. And why don't we just go ahead and do it? And it says, okay, so I'm glad that I made this mistake, although making mistakes is always frustrating. So related to the console, so I've run things and then I have my environment, and you can see very easily what the environment, what is already stored in memory. What have I already created? Created QT and QT full. I never ran line 8 in the console, and so because the line that I just tried to run quickly without thinking about it requires num steps, then I got an error. When you do a script, it starts at the top and then goes one by one down from the bottom, from the top to the bottom. We should really be running these things in order. So I will run. So I'm going to do that. Now it puts num steps in memory. And so now this should work. And it does. So we've got QT, RT. We have the number of steps. And the variable K is going to be the required storage at every time step. K sub t is what we're actually calculating when we do the Sequent Peak method. But we want to start this just with having 0 in it because we haven't actually done the calculation yet. So we'll just start the list by having all zeros. And I'll just make a note here that the final capacity is the maximum value of this. Okay. And so we'll just do this calculation for every one of the 18 time steps, and then we'll run a command that basically gives us the maximum value in that list, and then we'll be good to go. Now we are ready to actually start looping through the calculation just like you would do in a spreadsheet. So in a spreadsheet version of this, you would want to have a starting time step, then the subsequent time steps will be a function of that time step. The equation is k sub t equals r sub t minus q sub t plus k t minus 1, or k at the previous time step. And the idea behind that is that it is keeping a running total of the amount of storage that you need when you enter into a period where you have a deficit over the course of a couple of time steps. One thing that often comes up in equations like this is the fact that we're going to be running through t equals 1, t equals 2, t equals 3, t equals 4, up to 18, but we need something to get the process started. And there's different ways of doing this, but I'll show you a way that I typically use that seems to be decently straightforward, where I store a special variable that is just the previous time step. So we're going to get into a loop, and in that loop, the loop will start with that the first value, or the 0th value, the value to begin the whole process, and then it'll go and compound on itself as we go along. So I'm going to create a variable that is just going to be a single number. And that single number is going to be used in our calculation. It's going to change as we update. I'm going to call it k sub t prev, or just previous. So the previous k sub t value, and I'm just going to initialize that to be 0. For the very first time step, it will be 0, just like it would be in a spreadsheet. And then we will update that previous value at the end of the for loop such that we can use it then for every time step. So a for loop, a variable I that we are declaring right here, in a range of numbers that we wanted to loop through. And we'll explain how that loop works in a second, but it's 1 to number of steps. And then I'm going to make some brackets. The idea behind this is that the control in this program, again, starts from top to bottom. And you're going to need to look at the first value first, then the second value, then the third value, and the fourth value. And that's what for gives you. So when you start this, it says I is in this range. So I is going to start at number 1. So if I was to just print the value of I at line 21, it would just tell me, oh, I equals 1. Then when you get to the bottom of this control loop, so then when you get to line 22, it goes back to the top and it checks to see if it increases I, and then it checks to see if I is still in this range. If it is, then you repeat. And then if it's not, at the end you bump out and you leave the loop. So I is going to equal 1 here. And it's time for us to calculate K1. When t equals 1, we're going to figure out what is the desired storage at the first time step. So this equation is actually only valid if it is positive, and then k sub t equals 0 otherwise. So that's an important distinction that I forgot to mention. So k sub t is this only if it's positive. And there's different ways to do this, but what I thought I would do is I would just calculate the value first, and then I would check to see whether that calculated value is greater than 0 or not. Calculate k sub t regardless if it is greater than or 0 or less than 0. And I'm storing this not in an array, but just in a single value, because we'll save that single value into our list or our array later on. So just k sub t trial, and it's allowed to have whatever sign that it has. Is going to be the ith member of r sub t sub full. So in session 1, we talked about how to index data frames and how to index arrays. Here we're all working with arrays, and so we use the brackets with the index that we desire. And so I here is created in this for loop, and it's how we're going to index these arrays. So I want the ith value of r sub t sub full minus the ith value of q sub t sub full plus what? Well, it would be possible for us to say I minus 1 here, right? Because we want to have t minus 1. I could have used t in my index if I wanted to, but I is so common to use as an index that I default to I. But whatever the value that you declare here needs to be the same, obviously, as what you're doing here. I minus 1 is really what we want, but why is that a problem? I wish this was interactive, but maybe think about it for a second. The reason why it's a problem is because at I equals 1, we don't have an I minus 1. There is no 0th member of this array. The array starts at 1. There's different ways to get around it, like I said, but we've just created this k sub t sub previous variable to do it, so we'll just use that. K sub t sub previous. Right now we're fine because we know that this is 0 because we said it was 0 up here in line 18. When we get to I equals 2, we're going to need to work with that, but we'll see how to do that in a second. So the calculation that we've given you here is just going to give us what k sub t would be regardless if it was positive or negative. But we will only store it in this list that we have if it is positive. That's the second control that we're going to identify here. It's called an if statement. So an if statement just looks like this. It is if, and then there is a condition. And the condition is going to be if this k sub t sub trial variable that we just declared, if that thing is greater than 0, this is a Boolean operator that gives a test. So it takes this number, says if it's 0, if it is indeed greater than 0, then this returns 1, and you are allowed to do what is inside this block. Just like in life, if you clean your room, you get to play Nintendo, right? But then there's an else. There's always an else, right? And so if this condition is not met, we need to do something else. And so that's what an if statement, if-else statement is. If k sub t sub trial is greater than 0, we need to store the value of k sub t sub trial into our array. So we're going to do that. We're going to say k sub t sub full, the ith value of k sub t sub full. So now we're ready to actually store it. Because otherwise, this variable would just kind of go off into the sunset. You know, we're not storing it anywhere. It's just something that's going to keep getting rewritten over and over again. So we need to store it. K sub t sub full, the ith value of that is going to just simply be equal to k sub t sub trial, right? But otherwise, this else is going to fire if k sub t sub trial is less than 0, in which case we don't want to keep track of it. We want to just say that it is 0, which is the way that the Sequent Peak method works. And so we're just going to say k sub t full I equals 0. If we didn't do anything else, then when we get to the bottom of this, I is going to get higher. I is going to turn into 2. And we're going to go back up to the top. And then when we get to line 22, it's going to say this trial is going to get overwritten, which is fine. That's what we want. The second release, the second value of this inflow, but k sub t sub previous has not been overwritten yet. It's still going to be equal to 0, and so that would give you an error. To get ready for next step in process, store k sub t sub previous, because when you do these iterations, it's like today's fresh bread is tomorrow's day old bread, right? And it's the same thing. You know, when we get to I equals 2, we're going to want to say that the previous value came from I equals 1, right? And so k sub t sub prev is just simply equal to whatever it is at this time step, because we have not yet iterated. I is going to equal 1 in the first round of this all the way up to here, and then when it gets down to here, it's going to go and it's going to increment. So if we put this right here, then we're ready to go for the next time step. Just to repeat one more time, at first I equals 1, so then we are saving a trial of the I equals 1 release, I equals 1 inflow, and then this previous value that comes in from up here. We store it if it's positive. If otherwise, we say it's equal to 0. We get ready for the next time step by updating the value of the previous k sub t to being whatever it is now. And then when we go up to the top, I is going to equal 2. And so you're going to have the release 2, the flow 2, and then the kt from I equals 1, which we stored down here at the previous step. And that's it. It's going to go through all 18 steps, giving you values of k for all of those time steps. As I mentioned, the last step then is to say that the capacity is the maximum value of k, and there's a command for that, right? So I say capacity equals the maximum, which, guess what? It's just the max, right? That's just what the function is called. So max of kt full. When we do this, it's just going to store capacity in memory, and we can look in the environment up at the top to see what the answer is, but it's also nice to just plop the answer on the computer screen just so that we can check it. And you can also save it to a file and do all these other things. But for right now, I'm going to print the results to the screen. And lots of different ways to do this, but the cat command will work fine here. And so it just concatenates some strings together and then shows you the results. And so I like to just write something so that the result is in some context. So I say the capacity is for the first part of the string that I want to concatenate together, and then the second part is just the number for capacity. When you were working on this, and certainly when I was developing this example for you, when I was getting ready to make this video, you want to be testing things as you go. And you know, in this sequence of tutorials, we can talk about different ways to test things in RStudio and that kind of thing. But for the sake of argument, you've already seen how to run one thing at a time. I'm just going to go and run everything. When you run the selected lines, and I'm going to make the console bigger so that you can see, it actually repeats all of the code to you, which is nice because it's really just a matter, you know, running a script in R is really just a matter of kind of one by one inputting all these things. Like if you were to type this into the console, you would get the same result. So you have the inflows, the doubling, the number of steps, RT full, KT full, and then this for loop with the KT previous at the beginning, and then the thing. So you can see that our cat command has actually spit something out to the console again. So it says the capacity is 7.5. And if you're familiar with the book answer, then that is indeed the answer, right? So our program has succeeded. Remember from last time, we can use these view commands to actually show us the thing that is of most interest for our purposes is probably k sub t sub full. And when we do this, it just gives you a spreadsheet view of what k sub t sub full is. And as you could see from the textbook, what this does is it sort of shows you, just like we talked about in the beginning of this lecture, where you can just tell from arithmetic that you're going to be in trouble in the first 3 time steps because you don't have enough water. And k sub t shows you that, where right off the bat, you have 1 inflow, but you need 3.5, so you're down 2.5. And then you're down another 0.5, so the total amount of storage that you need in this case is 3. You're down another 0.5 in the next time step, and then you have, and then in the fourth time step, you kind of gain back some of the deficit that you have because you have 5 incoming water. You need 3.5 of that, but then some of that will actually offset the amount of storage that you need. So the amount of storage that you need goes down to 2. And then by the time you get to a time of plenty, so to say, where when you have enough storage, then the required storage goes down to 0. This would be considered one sojourn and a failure, so to say, where you're entering into a time where you would be needing to release water from the reservoir in order to function. That's the first time. And then you get into some good times. And then you get into the worst times, like Chumbawamba, good times, better times, bad times, worst times, what have you. So the real pain point, like I said, comes into that time when you've got 1, 1, and the sequence repeats with itself. So then you can see that the storage starts to increase, and it gets to a maximum of 7.5. And then you get down in and you're in the clear again, and then the sequence is going to start to repeat itself down here. So there you go. So it has given you 7.5. But the cool thing, and granted, you can do this in spreadsheets as well, but imagine if you had hundreds and hundreds of flow points and you wanted to do this. It documents the way that you did everything, so it gives you nice abilities to have these comments all over the place to show you, which is hard. If you've ever gotten a spreadsheet from somebody, you can tell, how did they do this? You have to go and pick around at every individual cell, where here it's all laid out. And then if I change one of these numbers, so I can just start to do kind of some sensitivity analysis where I can change one of these numbers, and it's as easy as running everything again. And I think, yeah, so I think that and we'll just check to see. So all I did was I just changed one of those numbers. That number is important because that used to be 8, right? And so that is really refilling your system for the rest of the time. And I just cut down the amount of flow that you have there. And so you can see that the QT has been updated, and that's all I needed to do. And I just hit a button and it ran the rest of it. And now it increased my capacity to 8.5. If you were to put this into a function, you would just have a function and be able to run through it as many times as you wanted. You could do thousands of these calculations just with a click of a button that would require some macros or some fancy stuff in spreadsheet land that would be kind of hard to do. So this is starting to hopefully this is starting to give you an appreciation for how moving beyond a spreadsheet can actually be beneficial, especially when even when the calculations are simple like this. But for more complicated calculations, it's even better. Hopefully the juices are sort of flowing a little bit associated with being able to automate things that are harder to automate in a spreadsheet, especially with R's power to actually pull data from places in a more automatic kind of fashion. You can do this in a spreadsheet, obviously, but it's starting to become more powerful if you were to kind of make it more systematic in a program like this. But a lot of the day-to-day usage of R for data analysts and that kind of thing is not really in writing these types of algorithms yourself, but it is in using some packages that people have developed that encapsulate a bunch of calculations in one place that you can kind of access. So in the next part of this sequence, we are going to explore a package in R that's actually called reservoir, that has a sequent peak calculation built into it, as well as a lot of other things. Now, every time that you use a package, you have to try to figure out what is the best way to use it, what kind of data types go into the functions, and there is an art to try to figure out how to do it. And so that's why it's worth spending a whole video on that. So that is what is going to come next in the sequence. But for the time being, that's it for me. Like, comment, and subscribe, and we'll see you next time.